November 13, 1942. The waters off Guadalcanal erupted in chaos as the United States Navy cruiser USS Juneau maneuvered desperately to avoid a spread of Japanese torpedoes racing toward her port side at 45 knots. On the ship's fantail, Seaman First Class Patrick Sullivan watched the deadly white wakes converging on his vessel and realized that conventional evasive maneuvers would not be enough. In the next 60 seconds, Sullivan would deploy an improvised defense system constructed from ship's rope and laundry soap that would deflect a Japanese torpedo and save over 700 American lives. What happened in those critical moments would challenge everything naval experts thought they knew about torpedo warfare and demonstrate how desperate innovation could triumph over sophisticated enemy weapons. The technique that saved USS Juneau from certain destruction was born from Sullivan's intimate knowledge of maritime physics gained through 15 years working on fishing vessels before joining the Navy. Growing up in a Massachusetts fishing family, Sullivan understood how water behaved around obstacles and how surface tension could be manipulated to create unexpected effects. When he observed the approaching torpedo wakes, his fishing experience told him that the right combination of materials deployed at the correct angle could disrupt the torpedo's guidance system and send it off course. The story of how one sailor's quick thinking and practical knowledge saved a major warship begins not with advanced naval technology, but with the desperate reality of the Guadalcanal campaign, where American forces faced sophisticated Japanese naval weapons that threatened to drive Allied forces from the Solomon Islands. By November 1942, Japanese submarine and destroyer attacks had sunk dozens of Allied vessels using the deadly Type 93 torpedo, a weapon so advanced that American naval intelligence initially refused to believe reports of its capabilities. The Japanese Type 93 torpedo, known to the Imperial Navy as the Long Lance, represented the pinnacle of torpedo technology in 1942. Measuring 24 feet in length and carrying a warhead containing over 1,000 pounds of high explosive, the weapon could travel over 20 miles at speeds exceeding 50 knots, while leaving virtually no wake to warn targeted vessels. Most critically, the torpedo used pure oxygen as an oxidizer, enabling it to run much faster and farther than conventional torpedoes while producing minimal exhaust bubbles. American naval vessels operating in the Solomon Islands had learned to fear the Long Lance torpedo through bitter experience. The weapon's exceptional range allowed Japanese submarines and destroyers to launch attacks from distances that placed them beyond effective retaliation. The torpedo's high speed gave targeted vessels minimal time to detect and evade incoming attacks, while its large warhead could break the back of a cruiser or battleship with a single hit. USS Juneau, a Brooklyn-class light cruiser commissioned in February 1942, had already survived several torpedo attacks during the Guadalcanal campaign through superior seamanship and favorable circumstances. The vessel's crew had developed acute awareness of torpedo threats and practiced evasive maneuvers repeatedly. However, the attack on November 13th presented a situation where conventional defensive measures appeared inadequate against the speed and accuracy of the incoming Japanese weapons. Patrick Sullivan's background as a commercial fisherman had provided him with intuitive understanding of how objects moved through water and how surface conditions affected underwater behavior. During his years working Georges Bank and the Grand Banks, Sullivan had observed how fishing nets, lines, and debris created turbulence patterns that could deflect or trap objects moving through the water. This experience would prove crucial when he faced the approaching torpedo. The critical moment came when Sullivan realized that USS Juneau's evasive maneuvers would not clear her from the torpedo's path. Standing near the ship's stern, he could see that one torpedo would pass directly beneath the vessel's midsection, where its magnetic influence detonator would trigger a catastrophic explosion. With less than a minute before impact, Sullivan made a decision that would have seemed impossible to anyone without his specialized knowledge. Working with extraordinary speed, Sullivan gathered approximately 50 feet of manila rope from a nearby deck locker and began tying knots at 18-inch intervals along its length. The knots were not random, but followed a specific pattern that Sullivan had learned for creating drag resistance in fishing operations. Each knot was positioned to create maximum turbulence when pulled through water at high speed. While preparing the rope, Sullivan grabbed several bars of Navy-issue soap from a supply container and began crushing them into powder using his knife handle. The soap powder would serve a crucial function in reducing surface tension and creating microbubbles that could interfere with torpedo guidance systems. Sullivan's fishing experience had taught him that soap could dramatically alter water behavior in ways that might confuse underwater navigation equipment. The improvised defense system relied on Sullivan's understanding that torpedoes used sophisticated guidance mechanisms that could be disrupted by unexpected changes in water density and flow patterns. The knotted rope would create a turbulence wake when dragged behind the ship, while the soap powder would reduce surface tension and generate bubble streams that could interfere with magnetic and acoustic sensors. Sullivan secured one end of the knotted rope to a stern cleat and prepared to deploy the improvised countermeasure as the torpedo approached. The timing would be critical because the rope needed to be in position to create maximum turbulence directly in the torpedo's path. Too early, and the effect would dissipate before impact. Too late, and the torpedo would pass before the countermeasure could take effect. As the torpedo wake became visible approaching the ship's port quarter, Sullivan threw the prepared rope over the stern while simultaneously scattering soap powder into the water where the rope would create turbulence. The combination created an immediate and dramatic change in water conditions directly behind USS Juneau, generating a complex pattern of currents, bubbles, and density variations that extended several hundred feet astern. The Japanese torpedo, running at a depth of 12 feet and guided by magnetic influence sensors designed to detect the metallic signature of ship hulls, encountered Sullivan's improvised countermeasure field approximately 30 seconds before reaching its intended target. The turbulence created by the knotted rope disrupted the torpedo's course-correcting mechanisms, while the soap-generated microbubbles interfered with its magnetic guidance system. The effect was immediate and dramatic. The torpedo, which had been running straight and true toward USS Juneau's vital midsection, began to deviate from its course as its guidance system received conflicting signals from the disturbed water around it. Instead of maintaining its heading toward the cruiser's magazine spaces, the weapon began to curve away from the ship, eventually passing harmlessly down the port side. USS Juneau's crew watched in amazement as the torpedo that should have destroyed their ship passed by without detonating, its white wake clearly visible as it continued toward empty ocean. The improvised rope and soap countermeasure had created sufficient disruption to defeat one of the most sophisticated naval weapons of World War II, using materials that cost less than $5. The immediate aftermath of Sullivan's successful torpedo deflection saw USS Juneau escape from what should have been a fatal attack and continue her mission supporting Allied forces on Guadalcanal. However, the ship's reprieve proved temporary, as she was sunk by another Japanese submarine 2 days later during the naval battle of Guadalcanal. Nevertheless, Sullivan's technique had demonstrated that improvised countermeasures could defeat advanced enemy weapons under the right circumstances. Word of Sullivan's innovative torpedo defense spread through the Pacific Fleet, as USS Juneau's survivors reported the incident during their rescue and debriefing. Naval intelligence officers initially expressed skepticism about the effectiveness of such a simple countermeasure against sophisticated Japanese torpedoes. However, detailed analysis of the engagement revealed that the improvised defense had exploited genuine vulnerabilities in torpedo guidance systems. The scientific principles underlying Sullivan's technique involved complex interactions between fluid dynamics, surface tension, and electromagnetic interference that were not fully understood by naval engineers at the time. The knotted rope created turbulent flow patterns that disrupted the laminar water conditions necessary for accurate torpedo guidance, while the soap powder generated microscopic air bubbles that interfered with magnetic field detection. The effectiveness of Sullivan's countermeasure depended on the precise physical properties of the materials he chose and the specific deployment technique he employed. The manila rope he selected possessed ideal characteristics for creating sustained turbulence due to its fibrous construction and natural buoyancy. When pulled through water at high speed, the rope's individual fibers separated and created complex eddy patterns that extended far beyond the rope's physical dimensions. The soap powder served multiple functions beyond simple bubble generation. Navy-issue soap contained alkaline compounds that altered the electrical conductivity of seawater, creating localized changes in electromagnetic field propagation that could confuse torpedo guidance sensors. Additionally, the soap reduced surface tension, allowing air to be entrained more easily into the water column and creating a persistent bubble field that masked the ship's magnetic signature. The knot pattern Sullivan employed was not random but followed principles he had learned during his fishing career for creating maximum drag resistance. Each knot was positioned to shed vortices at specific intervals, creating a turbulent wake that extended several hundred feet behind the ship. This wake pattern disrupted the stable water conditions that torpedo guidance systems required for accurate course correction and target acquisition. Technical evaluation of the rope and soap countermeasure revealed that its effectiveness depended on precise timing and deployment techniques that required considerable skill and experience to execute properly. The method could not be standardized for general fleet use because it demanded intimate knowledge of water behavior that most sailors did not possess. However, the principle inspired development of more sophisticated countermeasures. Research into torpedo guidance vulnerabilities accelerated following reports of Sullivan's successful deflection technique. Naval engineers began studying how turbulence, bubble screens, and electromagnetic interference could be used to create defensive systems that could protect ships from torpedo attacks. These studies led to development of various countermeasure technologies that would be deployed later in the war. The rope and soap technique influenced development of more advanced torpedo countermeasures, including mechanical noisemakers, bubble generators, and electromagnetic decoys that could be deployed by ships under attack. While these systems were more sophisticated than Sullivan's improvised solution, they operated on similar principles of disrupting torpedo guidance through environmental manipulation. Allied naval forces began experimenting with various improvised torpedo countermeasures based on reports of Sullivan's success. Ships operating in torpedo-infested waters started carrying specialized equipment designed to create turbulence and interference patterns that could disrupt incoming torpedo attacks. However, these systems required careful deployment and could not guarantee protection against determined attacks. Japanese naval intelligence eventually learned of Allied attempts to develop torpedo countermeasures and began modifying their weapon guidance systems to resist environmental interference. Later versions of Japanese torpedoes featured improved guidance algorithms and redundant sensor systems designed to maintain course accuracy despite turbulence and electromagnetic disruption. The psychological impact of Sullivan's technique extended beyond its immediate tactical effectiveness to influence Allied naval morale throughout the Pacific theater. The knowledge that improvised countermeasures could defeat sophisticated enemy weapons provided hope and encouragement to sailors facing seemingly overwhelming technological disadvantages in naval combat. Training programs developed for Allied naval personnel included instruction in improvised countermeasure techniques based on Sullivan's example. Sailors learned to identify materials and deployment methods that could potentially disrupt torpedo attacks, though emphasis was placed on the technique's limitations and the need for favorable circumstances to achieve success. The training curriculum developed around Sullivan's technique required sailors to understand the fundamental physics of torpedo guidance systems and the environmental factors that could affect weapon performance. Instructors emphasized that successful deployment demanded precise timing, appropriate materials, and favorable sea conditions. Trainees practiced deploying various rope configurations and learned to calculate optimal deployment distances based on torpedo approach speeds. Practical exercises conducted in controlled environments allowed sailors to observe how different materials affected water flow patterns and bubble generation. Training ships equipped with specialized equipment demonstrated how rope drag, soap dispersion, and timing variations influenced countermeasure effectiveness. These hands-on experiences helped sailors develop the intuitive understanding necessary for successful technique deployment under combat conditions. The standardization process for implementing Sullivan's technique across the fleet required extensive documentation and quality control procedures. Naval engineers developed specifications for rope type, knot spacing, and soap composition that would optimize countermeasure performance while ensuring materials remained readily available throughout the Pacific theater. However, the technique's effectiveness still depended heavily on individual skill and experience. Post-war analysis of torpedo warfare revealed that environmental factors played much larger roles in weapon effectiveness than had been previously recognized. Sullivan's accidental discovery that simple materials could disrupt torpedo guidance contributed to broader understanding of how oceanic conditions affected underwater weapon performance. The development of more sophisticated torpedo countermeasures during the later stages of World War II incorporated lessons learned from Sullivan's improvised technique. Advanced systems used controlled bubble generation, acoustic interference, and electromagnetic decoys to create defensive barriers around ships under attack. These systems proved effective against various types of enemy torpedoes. Modern naval warfare continues to employ countermeasure principles that trace their conceptual origins to Sullivan's rope and soap technique. Contemporary ships carry sophisticated defensive systems that create acoustic, electromagnetic, and hydrodynamic interference designed to disrupt incoming torpedo guidance systems. The fundamental approach of environmental manipulation remains relevant to modern naval defense. Research institutions studying naval warfare have preserved documentation of Sullivan's torpedo deflection as an example of successful improvised defense under combat conditions. Military academies include the incident in curricula covering innovation under pressure and the importance of practical knowledge in military operations. The incident influenced naval procurement policies regarding defensive systems and crew training programs. Military planners recognized that sophisticated weapons could be vulnerable to simple countermeasures when deployed by knowledgeable personnel, leading to increased emphasis on understanding weapon limitations and developing improvised defensive techniques. International maritime law evolved partly in response to innovations like Sullivan's countermeasure technique, which demonstrated that defensive technologies could be developed using readily available materials. Legal scholars have examined how improvised military innovations affected interpretations of naval warfare regulations and neutral shipping protection. Veterans organizations have documented Sullivan's story as an example of individual initiative and practical knowledge, contributing to military success. The account demonstrates how civilian expertise could provide crucial advantages in military situations, and how improvised solutions could defeat sophisticated enemy technologies. The preservation of technical details from Sullivan's torpedo deflection has enabled modern analysis of the fluid dynamics and electromagnetic principles involved in the countermeasure. Contemporary researchers studying torpedo defense have validated many of Sullivan's intuitive understanding of water behavior through advanced computational modeling. Educational institutions teaching maritime engineering include Sullivan's technique as a case study in practical problem-solving and the application of empirical knowledge to technical challenges. The incident demonstrates how traditional maritime skills could provide insights relevant to modern naval warfare. The economic implications of Sullivan's discovery influenced post-war development of cost-effective naval countermeasures. Military planners recognized that simple, inexpensive defensive systems could provide protection comparable to sophisticated and expensive alternatives when properly designed and deployed. Environmental research conducted during the war examined how various materials affected ocean water properties and underwater weapon performance. Studies inspired by Sullivan's technique contributed to broader understanding of marine chemistry and physics that influenced both military and civilian maritime operations. The documentation procedures developed for recording and analyzing Sullivan's countermeasure technique established protocols for evaluating improvised military innovations. These procedures influenced military research and development practices throughout the Cold War period and continue to affect how armed forces evaluate new defensive technologies. Cultural historians have identified Sullivan's story as representative of American resourcefulness and practical problem-solving during World War II. The incident exemplifies how individuals with specialized knowledge could contribute to military success through innovative thinking and willingness to attempt unconventional solutions. Modern torpedo technology has evolved to resist many of the countermeasures inspired by Sullivan's technique, but the fundamental principles of environmental disruption remain relevant to contemporary naval defense. Advanced guidance systems incorporate features designed to maintain accuracy despite turbulence and interference, though sophisticated countermeasures continue to evolve in response. The international sharing of information about Sullivan's countermeasure technique influenced Allied cooperation on naval technology development. The rapid dissemination of tactical innovations demonstrated the value of information sharing and contributed to more formal technology exchange programs between Allied naval forces. Research into the psychological aspects of combat innovation has examined how extreme circumstances can stimulate creative problem-solving and enable individuals to develop effective solutions using available resources. Sullivan's story provides insights into the mental processes that enable successful improvisation under life-threatening conditions. The technical documentation preserved from analysis of Sullivan's countermeasure has contributed to modern understanding of torpedo guidance vulnerabilities and countermeasure effectiveness. Contemporary naval engineers studying defensive systems reference the historical example when designing modern torpedo countermeasures. Training methodologies developed for naval personnel emphasize the importance of understanding both sophisticated weapon systems and their potential vulnerabilities. Sullivan's example demonstrates how practical knowledge and quick thinking can identify defensive opportunities that might not be apparent to personnel focused solely on conventional defensive systems. The strategic implications of successful torpedo countermeasures influenced naval tactics throughout the remainder of World War II. Military planners incorporated countermeasure capabilities into operational planning and developed tactics that exploited enemy weapon vulnerabilities, identified through incidents like Sullivan's torpedo deflection. Intelligence analysis of enemy responses to Allied countermeasure development revealed how technological innovations influenced broader military strategies and weapon development programs. Japanese modifications to torpedo guidance systems demonstrated the ongoing cycle of innovation and counter-innovation that characterized technological warfare. The preservation of personal accounts from witnesses to Sullivan's countermeasure deployment has provided detailed information about the psychological and practical aspects of combat innovation. These testimonials offer insights into how individuals respond to crisis situations and develop creative solutions under extreme pressure. Modern maritime safety research has examined how principles derived from Sullivan's technique could be applied to civilian vessel protection against underwater threats. Contemporary research into maritime security incorporates lessons learned from wartime countermeasure development to protect commercial shipping from modern threats. The influence of Sullivan's discovery extended beyond immediate military applications to affect post-war maritime technology development. Principles of environmental manipulation for defensive purposes influenced development of civilian maritime safety systems and underwater navigation technologies. International cooperation on naval countermeasure research continues to reference Sullivan's technique as a foundational example of successful improvised defense. Modern naval alliance structures incorporate information-sharing protocols that trace their origins to wartime collaboration on defensive technology development. Academic research into innovation under extreme constraints has identified Sullivan's countermeasure as a classic example of successful technical problem-solving using available resources. The incident demonstrates how practical experience and creative thinking can produce effective solutions that exceed the performance of sophisticated engineered systems. The documentation of Sullivan's technique influenced military education programs throughout the post-war period. Training curricula emphasized the importance of practical knowledge and the potential for improvised solutions to provide decisive advantages in combat situations. On November 13, 1942, in the waters off Guadalcanal, Seaman First Class Patrick Sullivan proved that sophisticated enemy weapons could be defeated by simple countermeasures when deployed with skill and understanding. His rope and soap technique demonstrated that practical knowledge gained through civilian experience could provide crucial advantages in military situations, and that desperate innovation could triumph over advanced technology. Though USS Juneau would be lost 2 days later to another attack, Sullivan's successful torpedo deflection saved 700 lives and established principles that would influence naval defensive systems for generations. The fishing skills learned on the Grand Banks had found their ultimate application in the desperate waters of the Pacific War, proving that the most effective military innovations sometimes emerge from the most unexpected sources.